Well, so far we have discussed about evaluating properties of substances in the cases that we have tabulated data for them. But that's not the case for most of the liquids, all of the solids, and some cases of superheated gases. For those cases, we need to estimate the properties in other methods. So let's begin by subcooled liquids. In your textbook, you have a table A5, for compressed liquid water. The reason why we have tabulated the data for water in compressed liquid phase is lots of the applications that water have in the industry. But for many materials, like for instance, ammonia or refrigerants, we don't have subcooled liquid tables. Instead, we use the tables of saturated liquid in those cases to estimate the properties in subcooled liquid phase. And here is the equation for it. That's a super simple equation. Look at this graph, the graph that we have here, the temperature versus specific internal energy of a material. If you look at this graph, we exaggerate these graphs indeed. In this graph, in reality, a line for an isobaric process is really something like this. Let me draw one here. It is something, oh, my apologies. Oh, let me go here and choose my pane. Here it is. Okay. And this is my line. Medium is strong. Okay, good. Let me see where the page was. Okay, Control Z. Oh, here we go. Okay. In reality, the line is something like this. It is very, very close to saturated liquid line in the left-hand side, right? We just exaggerated to make it that what we're talking in the left-hand side. But if we don't exaggerate it, you will see that the line of the constant pressure is very, very close to saturated liquid line, which suggests that, as seen here, the properties at this region can be estimated with the properties of the saturated liquid at the same temperature. For instance, the internal energy at this subcooled liquid can be estimated by the internal energy at 80 degrees Celsius on the saturated liquid line. That is what we are showing here, right? Let me erase this one and you can see clearly what I'm talking about, okay? So with that said, we use a simple equation. We say that in subcooled liquid region, just focus on the temperature. See what the temperature is. Go to the saturated liquid tables that are tabulated based on temperature. And then find the properties of saturated fluid at the same temperature. For instance, here, look at this equation, right? The specific volume of a subcooled liquid equals a specific volume of the saturated fluid at the same temperature. So on and so forth for internal energy and enthalpy. With the enthalpy, however, we have two equations. One estimate is to say that H is equal to HF at the given temperature. We can be more precise and use this second term. In the second equation, we have one extra term. And let me just bold this extra term. Here is our extra term. we can actually use the same estimate, but we can modify it with this extra term. H equals HF at the same temperature plus the specific volume at the given temperature times the given pressure minus the saturation pressure at the same temperature. Usually the second term is negligible compared to the first term, except for the cases that we are dealing with, for instance, pumps. In pump and pumping devices, the second term is important because the change in the pressure is important. Okay, we have huge changes in the pressure in the pumps, so this term in the pumps are important and we should consider it. But in most of the cases, we can neglect this term. Now let's look at one example together and see how we use these estimates. Refrigerant 134A is given at 8 bar and 20 degrees Celsius. I want you to find the specific volume and the specific enthalpy of this refrigerant at given condition. Please pause your video for 10 minutes now and try to solve it yourself. Then you can return and watch how I solve this problem, okay? All right. To solve this problem, I begin by referring to the index of tables in SI units, page 925, to see what table I have to use. Okay, so my first step is step 1, refer to index of tables in SI units. And this is in page 925. Okay, let me go over this table and we can see it together. Let's go over the textbook together. Here is our textbook. Page 925. If you look at this table, I'm dealing with properties of saturated refrigerant 134A. And I told you that we are gonna check always, we are going to check the temperature tables, right? The temperature tables are table A10 in page 943. So my second step is to go to table A10, page 943. Let me write down here. Second step, look at table A10 in page 943. Let me see what I have in this page. I go to page 943. Keep in mind that I don't know beforehand if my properties are saturated liquid, they are subcooled liquid, superheated vapor, or what. So I need to define the phase of the material at the first step. Okay, in this table, what was my conditions? Let me review again. It was 20 degrees Celsius, 8 bar, 20 degrees Celsius. All right, here we go. At 20 degrees Celsius, as you see here, this is 20 degrees Celsius. Oh, my apologies. Here is my 20 degrees Celsius. I can show it. I don't know if it is, it's not highlighting it. Let me open it in. No, let me open it in this software so that I can highlight it. Okay. All right, at 20 degrees Celsius, if you look at it. All right, here we go. Okay, perfect. I'm gonna go to page 943. And let's see what we have here. Okay, here is my table in page 943. Let me full screen it. View full screen. Oh, here we go. Page 900. Oh, Control Z, Control Z. Here we go. At this condition, this is the pressure that I have. This is the temperature that I have. Let me just show it here. Okay. This is my 20 degree. At 20 degree, you can see that the saturated pressure is 5.716. Okay, so saturated pressure is 5.716. My pressure is 8 bar, which is about this. That the pressure is above the saturated pressure at 20 degrees Celsius means that my condition is actually subcooled liquid, right? I am in subcooled liquid region, so with that said, the specific volume is the specific volume of the saturated liquid at this temperature. Look at the saturated liquid. Here is the saturated liquid, right? Look at this one, okay? And in my table, it says that it's a VF times 1,000. Whatever you read in this column is multiplied by 1,000, okay? Keep that one in mind. So specific volume is 0.8157, but it is multiplied by 1,000. So let me go and write down the result. Control L. You can see better. Okay, 3. So at T equals 20 degrees Celsius, we found out that P saturation was 5.7 bar, which is less than 8 bar. And it means that we have subcooled liquid. Okay, in your homework and exam, I want you all to prove what the state of, what the phase of your material is at the first step, and then you can go and find the properties. Now that I know it is subcooled liquid, I can tell that V of the subcooled liquid, V, oh, Control Z, my apologies. Okay, V is about VF at 20 degrees Celsius. And VF from that table, I know that VF times 1,000 equals 0.8157 cubic meter per kilogram, from which I can find out that V is 0.8157 times 10 raised to power negative 3 cubic meter per kilogram. The specific volume is somewhere around 0.8 liter per kilogram. Right? For the water, it is 1 liter per kilogram in atmospheric condition. This is this one is less denser than water. Oh, this is denser than water, so its specific volume is some 20% less than water in the room conditions. All right. That is for V. Also for the H, keep in mind that for H we have 2 estimates. The first estimate was this: H is about HF at the given temperature at 20 degrees Celsius. And you can see that HF from that table is 77.26 kilojoules per kilogram. This is the first estimate. Now I want to also evaluate the enthalpy using the second correlation, just to double check and see if there is any considerable change in the evaluation of the enthalpy. Let me choose another color so we can see it in a different color. This is my second estimate for enthalpy. Okay, and this is specific enthalpy. No, okay. My second estimate said me that H is HF at the given temperature plus the term that considers the effect of the pressure, P minus P sat. All of them are at the given temperature, okay? I plug in the values, H equals, HF was 77.26 kilojoules per kilogram plus VF was 0.1863 times my apologies. Control Z. It was 0.8157. 0.8157 times 10 raised to power -3 cubic meter per kilogram times, pay attention to the units of the pressure. Pressure is tabulated based on the bar. I need kilo because here I have kilojoules per kilogram. I want to generate a kilo here, so I convert that bar to kilopascal. My pressure is 8 bar, which equals 800 kilopascal, minus the saturated pressure was 5.71 bar, which equals 571.6 kilopascal. Let me write it, 0.6 kilopascal, okay? And with that said, let me escape the full screen. I think we need to add one more page. Let me go to edit, pages, and append one more page. Okay, here we go. All right, H equals, if you do the math, H will equal 77.26 kilojoules per kilopascal plus 0.1863 cubic meter kilopascal per kilogram. And if you convert the units, you will see that both of them are the same, right? Okay. So here, this is kilojoules per kilogram. Okay, here is kilojoules per kilogram, and you will see that the units are the same. So H equals, I can sum them up, and it will be 77.45 kilojoules per kilogram. This is more accurate estimate of the enthalpy, and as you see, the difference is something around 1 to 2%, right? Less than 1%. So I don't know how much. Maybe just a few point of the percent. We can do the calculation. Okay, it's some 0.2% change in the estimate of the H. So it's for most of the calculations, this amount of accuracy is unnecessary, and we can just neglect that correcting term. All right, this is how we estimate the properties of subcooled liquid using the saturation table at the same temperature. Before we go forward, I want to introduce you another property. Let me take this. Let me just full screen this. The next property that I want to introduce you, and this also an intensive property of a material, is the specific heat. With the specific heat, we mean, and this is for very specific case. In a specific case of a constant volume experiment, provided that we have a constant volume of a material, if we heat up it so much that the temperature of the material inside this constant volume tank increases by 1 degree Celsius, the amount of heat consumed is called constant volume specific heat, and we denote it by CV. For instance, the CV for one material might be 3.12 kilojoules per kilogram degree Celsius, meaning that in order to increase the temperature of 1 kilogram of this material by 1 degree Celsius in constant volume, we should use 3.12 kilojoules of the heat. And the other test that we can do is similar, except that instead of using a constant volume tank, we can use a constant pressure piston cylinder. In which case, for the same material, the amount of the heat that we consume is more, obviously. Cp, or the constant pressure specific heat for any material, is always more than Cv. And the reason for it is obvious in this picture, because Cp is the heat that is consumed to both increase the temperature of the material by 1 degree Celsius and simultaneously to expand the material, right? It is expand because it's in a cylinder piston device. So for the same material, for instance, Cp equals 5.19 kilojoules per kilogram degree Celsius. Then later in future chapters, we will define Cp and Cv in more precise way. But for now, this is enough. Just keep in mind that Cp and Cv are also properties of pure substances. They change by the temperature and pressure, like all other properties, but for most of the cases, their change is not that much. So we can consider that they are pretty much, close to an average values. Specifically, for the case of incompressible materials, Cp and Cv are always constant. And this is what we're going to talk about today. An incompressible substance is a substance whose specific volume or density is constant, right? For instance, liquids. We know that the specific volume of a liquid changes slightly by pressure. For instance, the density of water under huge pressure, right? Like the density of water at the floor of ocean is higher than the density of the water on the earth, right? That's because of the huge pressure applied over there. But even under such a huge pressure, the change in the density of water is really negligible. So we can tell that by very good accuracy. The density and hence the specific volume of liquids are constant. Okay, it doesn't change that much. And definitely the same goes with solids. With the solids, no matter how much the pressure is, their density is pretty much constant. So for an incompressible substance, Cp and Cv are equal, and we always denote them by just C, right? Specific heat of incompressible materials is constant, and we have tables for them. You can use those tables. With these substances, we have two important equations. One of them is to evaluate the change in the internal energy, and we use this in analyzing closed systems. You remember in closed systems, we said that the change in the energy, right, Q minus W equals delta U. Let me write down it here. For a closed system, right, for a closed system, we said that Q minus W equals M times m times U2 minus U1 plus potential energy 2 minus potential energy 1 plus kinetic energy 2 minus kinetic energy 1. All right? Now, if in our closed system, we are dealing with an incompressible material, like for instance, a slab of aluminum, or I don't know, 2 liters of water. In that case, we can estimate U2 minus U1 with this simple correlation. U2 minus U1 equals C times T2 minus T1. Meaning that for incompressible substances, the change in internal energy is a function of only and only temperature. If the temperature changes, the internal energy increases. If the temperature drops, the internal energy is also going to drop. Likewise, for open systems, we discuss about the change in the enthalpy. And the change in the enthalpy equals C delta T plus V times P2 minus P1. Again, keep in mind that although H is a function of both temperature and pressure, but in most of the cases, the term of the pressure that I have underlined here, V times delta P, is negligible compared to the first term, except for the case of the poems. Because in the poems, the change in the temperature is very, very small, and instead, the change in the pressure is very high. So for the case of pumps, when we are analyzing, for instance, a liquid pump, an oil pump, milk pump, oil, whatever, in those cases, the second term V delta P is the dominant term. For the rest of devices, like for instance, a turbine or whatsoever, the first term, right, C delta T is usually the dominant term. All right, with that said, let's go over one last example. This is example, oh, my apologies. This should be example 4. Okay, let me correct this one. This is example 4. Example 4, here we go. I actually added one example, so I'm going to upload this new presentation file with the notes on it on Canvas so that you have the notes as well. But what do we want to solve here? A 5 kilogram aluminum rod undergoes a process from 300 Kelvin and 3 megapascal to 700 Kelvin and 30 megapascal. Calculate the change in the rod's total internal energy and enthalpy. The internal energy and enthalpy associated with the total mass we mean. All right. Again, please pause your video and give yourself 10 minutes to solve this problem. After you solve the problem, return back to watch how I solve the problem, okay? Well, to solve this problem, I begin with the same procedure. I begin by going over the index of the tables, find the appropriate table, and then I read the properties from the table and try to solve it. The first table that I have to look at is the index to tables in SI units, page 921. So step 1, I go to index to tables, and because everything is in SI units, I use the SI tables, SI units, and this is in page 925. If you go to that table, and let me show the table. Here we go. I think we have it here. All right, let me go to page 925. In this table, if you look at table A19, here it is. This is table A19. Look here, here we go. properties of selected solids and liquids, CP, rho, and K. Page 960. So I should go to page 960. Let me go to page 960 and then see what we have for aluminum. This page for aluminum, here it is. Look at this, aluminum. Oh, all right, the very first material here. I have aluminum here, and I'm going to read the properties of the aluminum. For the aluminum, two properties that are important for me are the specific heat, or CP, and its unit is kilojoules per kilogram Kelvin. I write this one, CP equals 0.903 kilojoules per kilogram Kelvin. I also need density. Rho is 2700 kilogram per cubic meter. Okay, I don't need thermal conductivity, so I'll leave it here. Let me go back to my problem and write down these properties. So step one, from page 9205, I found out that I need to go over table A19. All right, in page 960. Now, from page 960, step 2, I read these properties. Aluminum at 300 Kelvin, the properties that I've found was, my apologies, let's go to the previous page. Okay, here we go. CP equals 0.903 kilojoules per kilogram Kelvin, and rho is 2700 kilogram per cubic meter. Okay. All right, let me go to the next page. Now I'm looking for change in the internal energy. U2 minus U1 equals C T2 minus T1. And if you plug in the values, delta U will equal 0.903 kilojoules per kilogram Kelvin times 700 Kelvin was my final temperature, minus 300 Kelvin was initial temperature. And with that said, delta U equals 361.2 kilojoules per kilogram. I'm looking for total change in the internal energy, and we know that delta U capital equals M delta U lowercase. So delta U capital equals 5 kilograms times 361.2 kilojoules per kilogram, and this equals 1806 kilojoules. All right, so in order to increase the temperature of this aluminum bar from 300 Kelvin to 700 Kelvin, we need to heat it up by 1806 kilojoules of heat. Okay, for the next part, H2 minus H1 equals C T2 minus T1. My apologies, let me just erase this one and write it again in a more fashionable way. This is T2 minus T1 plus the second term V times P2 minus P1. But keep in mind that V is 1 over rho, okay? And we know that from previous step, we found out that U2 minus U1 equals C T2 minus T1. These are the things that I calculated from the next one. So if I substitute them in this, let me label it as star. If I substitute these two in the star, I will have H2 minus H1 equals U2 minus U1 plus delta P divided by rho. The change in the pressure divided by rho. So here we go. And now I can go and plug in the values. Delta H, I just need to pay attention to the units. Delta H equals, from the previous step, I found out that delta U was 361.2 kilojoules per kilogram. Pay attention that I'm writing the specific enthalpy and a specific internal energy plus, and I'm going to convert this to joules, so I'm going to multiply by 1,000 joules per 1 kilojoule, plus the term of the Control Z. Now let me just maximize the page. Plus the term of the pressure was, my pressure was in, let me just erase this one, write everything in. I'm going, instead of this one, I'm going to write everything in kilo. It will give me an easier time. Okay, this is in kilojoules, so this is in kilojoules, so I write pressure in kilopascal. Delta P was, final pressure was 30 megapascal, which equals 30,000 kilopascal minus 3 megapascal, which was 3,000 kilopascal, divided by the density is 2,700 kilogram per cubic meter. Now everything is in metric units except that I have a kilo for both of them, right? I have a kilo, let me show you. I have a kilo here. I have a kilo here, and I also have a kilo here, right? The rest of the things, all of them are in metric units. So delta H will be also in kilojoules per kilogram Kelvin. And if you do the math, you will find delta H equals 371.2 kilojoules per kilogram. Okay, you do the math yourself and you will find this number, 371.2 kilojoules per kilogram. Okay, well, if you check this one and you compare this number without with and without the second term, the correctest term V delta P, you will see that the effect of this second term is less than 3%. Okay, in this problem, the effect of this one will be less than 3%. So in some cases, you can just ignore that term. Finally, we are looking for total enthalpy. Delta H is M times lowercase delta h, and if you multiply the numbers and do the calculation, 5 kilogram times 371.2 kilojoules per kilogram will give you 1856 kilojoules. All right, and I'll leave the substitution of the mass and doing the calculation to you. All right, let me save this one and get out of here. Okay, with that said, we are going to conclude our lecture 9. In this lecture, we learned how to estimate the properties of saturated liquid vapor mixture in the first part of the lecture, and today we learned how to estimate the properties of the subcooled liquid using the saturated table. Keep in mind that for the water, specifically for the water, we have a table for subcooled liquid, and you have to use that table for the case of the water liquid, right? It is table A5, compressed liquid water, okay? So for the water, you have the tables, but for all other materials, when you are dealing with the subcooled liquid, we are going to use the estimates that we learned today. Also, we discussed about the specific heats, and we learned how to use the concept of a specific heat to calculate the change in the internal energy and enthalpy of incompressible materials, including solids and liquids. In lecture 10, we will go over using the theory of gases, the ideal gases, in order to estimate the properties of materials in superheated region, again, for the cases that we don't have tables, all right? In cases that we have no table for superheated region, we're gonna use the ideal gas theorem, and sometimes we're gonna need to modify that theorem to find a better estimate. That's the end of today's lecture. I'm going to upload the homework for this chapter, and I would like all of you to go and complete that lecture. Next week, we are going to have a quiz from what you have learned in this chapter. All right? Good luck.